Hello, and welcome to this video about eigenvector proofs. This is a fast test to see whether a 2x2 matrix is diagonalizable or not. Since this property isn't a definition, but a property of matrices that naturally arises, then it isn't easy to find a simple test for it. But I've found a fairly simple test for 2x2 matrices, and there's a nice trick that makes it work simply for these matrices and not for larger matrices. We would like all matrices to be diagonalizable, because it would make all of the mathematics a lot easier. But mathematical reality isn't always what we'd like it to be. So let's start this proof. If this matrix A has two distinct eigenvalues, then it's diagonalizable. An eigenvalue has to have at least one eigenvector to be an eigenvalue, because that's part of its definition. So there are two eigenvalues giving us two eigenvectors, and that's enough to diagonalize the matrix. Now we come to the case where A has only one distinct eigenvalue, which is more complicated. Then A is equivalent to only two possible matrices. The first matrix, which is a diagonal matrix with only one value gamma in its diagonal, or the Jordan canonical matrix with gamma in its diagonal and an extra one in the top right hand corner, in which case it isn't diagonalizable. So I'll just make some more room on the screen. We'll investigate the case where A has only one distinct eigenvalue. And these are the two cases for this happening. So we'll investigate the first case, where A is similar to this first matrix. This is the definition of similarity. It isn't row equivalence, but a sort of conjugated equivalence. So we have to simplify this expression. We can get the scalar term out in front. Then the identity matrix can be eliminated, because it's the matrix equivalent of 1, and 1 can be eliminated with multiplication. And so this inverse pair will cancel out to give us the identity. So A is equal to this matrix that is a diagonal matrix with only gamma in the diagonal. So if A is similar to this matrix, then it must be equal to it. And so if A has only one distinct eigenvalue and isn't equal to the diagonal matrix, then it must be similar to the other matrix that's the matrix in Jordan canonical form, with a 1 in the top corner, and is therefore undiagonalizable. So I'll just start with a clear screen with the two cases of A at the top. We can now say that if A isn't this diagonal matrix, then it must be similar to this Jordan canonical matrix. And this implies that it's not diagonalizable. We can then make this logical step that all matrices that can't be diagonalized must have only one distinct eigenvalue and not be the diagonal matrix gamma I. This means that the characteristic polynomial of this matrix must only have one distinct root. I'll just scroll everything up the screen so as to make more room. So now to calculate this characteristic polynomial, it's equal to this. The variable lambda is the independent variable of this polynomial. So the determinant of this matrix is equal to this, which will give us the characteristic polynomial. Simplifying this equation gives us this polynomial. To find the roots of this polynomial, we'll have to set this polynomial equal to 0 and solve for lambda. So we'll just write it out as this polynomial equal to 0. And we'll solve it using the quadratic equation like this. This gives us the eigenvalues of matrix A. So I'll just scroll everything up the screen like this to make some more room. If we want to have only one distinct eigenvalue, then this term under the square root sign must equal 0. We'll simplify this expression by calculating the square of this term and expanding these brackets. We can add these terms together to get this equation. We can factorize one of these expressions to get this equation, which is the most compact way of writing it, despite not being the most simplified. So this is the condition for a matrix to only have one eigenvalue. And then we have to join it to this condition, that it can't be equal to the diagonal matrix gamma I. So these are the two conditions for a matrix to not be diagonalizable. I'll just write it out as a logical statement like this. So I'll just scroll everything up the screen to make more room. If this matrix is to be non-diagonalizable, it must satisfy both of these math statements, this equality and this inequality. And we can write out this matrix inequality in terms of the entries of matrix A. If a matrix is to be diagonalizable, then the opposite or complement of this statement must be true. And this is the complement. We'll just get the complement of each math statement and replace the AND with an OR, so either of these statements being true will mean that the matrix is diagonalizable. We can replace the matrix equality with these scalar math statements. We don't need this statement to be there, because diagonal matrices with different eigenvalues are diagonalizable too. So we can get rid of it, and then we're left with this statement, which concludes this proof. And it's a very compact way of determining whether or not a 2x2 matrix is diagonalizable. It's not that straightforward for larger square matrices, and I don't know whether we'll ever get a test for a square matrix with a generalized size, like for an n by n matrix, but I hope one day we might. So I hope that you've found this video to be helpful and interesting. Please click like and subscribe if you did. Feel free to post up anything helpful in the comments and to share this video. And thanks a lot for watching.